Hello. Uh, yeah. Hello. So in today's class, we are going to start with some of the concepts that we have used in our previous session, and then we will move ahead. So we will start with these particular processes that we have learned. So we know that work done W. When work is done by the system, so we take it as dW is equal to minus PdV, correct? So in case of isobaric process meaning pressure is remaining constant. So pressure is remaining constant, volume is changing from V1 to, this is my V1 volume, this is my V2 volume, but pressure is remaining constant. So in this case, work done by the system W1 to 2 is equal to minus of PdV, where integration is starting from V1 and ending to V2, initial to final. So if we integrate this, we get P into minus of P into V2 minus V1. So work is P into V1 minus V2. Similarly, we have learned this for isochoric process. So what does isochoric process means? Choric meaning constant volume. So let's say at constant volume V, uh, I am getting I am going from pressure P1 to pressure P2. So work done will be minus P dV. So V is remaining constant. So this integration is going to be 0. So in case of isochoric process, work is equal to 0. There is no work done on the system, work done by the system. So W is equal to 0. Now, in case of any isothermal process meaning temperature is remaining constant for ideal gas. So for isothermal process, PV is equal to constant. So I am starting with P1, pressure P1 with some volume V1 and pressure P2 ending at pressure P2 with some volume V2. So as pressure is reducing or pressure is increasing, volume should behave in reverse way. So here pressure is more, volume is less, pressure is less, volume is more. So W I will get it as minus of P dV V1 to V2. So P for an ideal gas, what is P? PV is equal to RT. So I can replace P as RT by V into dV. So negative of RT ln 1 upon V is ln V. So ln V2 by P1 or ln P1 by P2. Okay, so this is work done by the system. And for isothermal process, it is going to be minus RT ln V2 by V1. Now, similarly, in case of adiabatic process, for adiabatic process, let's say it is going from P1 V1 to P2 V2. So for adiabatic process, we know that P into V raised to N remains constant. So I can replace P with some constant K divided by V raised to N dV. So constant comes out and 1 upon V raised to N, integration is V raised to minus N plus 1 divided by minus N plus 1 V1 to V2. So it will be K upon 1 minus N V2 raised to 1 minus N minus V1 raised to 1 minus N. Okay. So this I can replace K as P1 V1 raised to N. So I get it as, okay, there should be, okay. So I get this formula W is equal to P1 V1 minus P2 V2 divided by N minus 1 in one way. And in another way, if I divide by this V1 raised to N here, so I get my equation in this term P1 V1 divided by N minus 1, P2 by P1 raised to N minus 1 divided by N minus 1. So this is in case of adiabatic process. So in case of there are many ways to derive this equation. So for adiabatic process, you know that dq is equal to 0. There is no heat transfer between the system and its surroundings. So dq is equal to 0. So du is equal to dw. So for du, what is du? Du is always cv dt. So my w is equal to delta u, which is equal to cv delta t. And we can also define R as Cp minus Cv. So R divided by Cv is Cp divided by Cv minus 1. So R by Cv is gamma minus 1. So I can replace this CV as R divided by gamma minus 1, and I can find W is equal to R divided by gamma minus 1 delta T, or R into T2 minus T1 divided by gamma minus 1, that is equal to W, that is equal to delta U. For adiabatic process, W is equal to delta U. Now if we replace, for ideal gas, PV is equal to RT. So P1 V1 is equal to RT1, and P2 V2 is equal to RT2. So RT2 minus RT1, I can write it down as P2 V2 minus P1 D1 divided by gamma minus 1. This is one way of deriving it. Then further, from this you can derive, or you can write down the expression in this term: T into V raised to gamma minus 1 is constant, T into P raised to 1 minus gamma by gamma is constant, and P into V raised to gamma is equal to constant. And this is used for ideal gas with constant heat capacities undergoing mechanically reversible adiabatic expansion or compression. Okay. So it's just some another way of writing P1 V1 divided by gamma minus 1, P2 by P1 raised to gamma minus 1 by gamma minus 1. Okay, so what is this gamma? Gamma, we have defined it as Cp by Cv. So for any monoatomic gases like helium and argon, gamma can be taken as 1.67. Then for some diatomic gases, N2O2, gamma can be taken as 1.4, and for simple polyatomic gases, gamma can be 1.3. Now, polytropic. So what does polytropic mean? Polytropic meaning turning many ways. So we are just defining P into V raised to delta is equal to constant. So now let's say, so see, these are various ways. Okay, so let's say I am saying that delta is equal to 0. So delta is equal to 0 meaning P is equal to constant. So what does P is equal to constant means? Isobaric process. So delta is equal to 0 for isobaric process. Now let's say I am saying that delta is equal to 1. What does delta is equal to 1 mean? 1 meaning P into V is equal to constant, and PV is constant for isothermal process. So delta is equal to 1 for isothermal process. Now let's say delta is equal to gamma. So P into V raised to gamma is constant. So that is true for any adiabatic process. P into V raised to gamma is equal to constant. And for any isochoric process, delta can be infinite. Delta can be very, very high, infinite. Okay. So this is the for polytropic process. Delta is equal to 0, isobaric. Delta is equal to 1, isothermal. Delta is equal to gamma, adiabatic. And delta is equal to infinity for delta is equal to infinity for isochoric process. And similarly, these equations are also there. Then work done is also here. If I put delta is equal to 1, so sorry, if I put delta is equal to 0, if I put 0 here, no, okay. There are some limits we need to know. Okay, so this is something you need to remember. For constant V, delta can be plus minus infinite. Okay, so this is all about it. Now, then we had learned the first law of thermodynamics. We have derived it. Although energy assumes many forms, the total quantity of energy remains constant, and when energy appears in one form, it simultaneously appears in the other forms. So that's why energy of the universe remains constant. So delta of energy of the universe is 0. So that's for universe is consisting of system plus surrounding. So delta of energy of system plus delta of energy of surrounding is equal to 0. So total energy delta of U plus kinetic plus potential energy is equal to plus minus Q plus minus W. In our convention, heat added to the system is positive, heat removed from the system is negative. Then work done or work added to the system is positive, and work removed or work done by the system is we are taking as negative. So for closed system, we don't have kinetic potential energy terms, or so no changes in that. So delta U is equal to, we can write delta Q plus delta W. So this delta symbol is, del symbol is for path functions. For isolated system, so there is no temperature change, so there will be no heat added to the system. So delta E is 0. So del Q is equal to minus del W. Now we have also learned this for open system, where so let's try to have a look this from here. open system we have derived it, so that we are going to use uh, currently. So that's why I'm showing that. So see, mass flow rate m dot, molar flow rate n dot, and volumetric flow rate q, velocity u. So mass flow rate can be u into a into rho. So two streams m1 dot and m2 dot, they are entering to the control volume, and m3 dot is leaving to the control, leaving from the control volume. So as we are saying that mass is conserved, so mass d m by dt of control volume plus delta of mass flow rate is equal to 0. So it is nothing but input minus output. So we can say that at steady state, rho u a is equal to rho 1 u1 a1 is equal to rho 2 u2 a2. So that remains constant. Then if we look this for open system, so you can see each unit mass of a stream carries with it a total energy U, that is its internal energy, half U square, that is because of kinetic energy, and GZ, that is because of elevation. Okay, so we can write that d into mu by dt of control volume is equal to in u plus half u square plus gz, that is entering to the system with its mass flow rate, minus the same quantity u plus, here u should be capital, u plus half of u square plus gz into m dot, that is moving out of the system, plus some heat added to the system, some plus some work rate. Okay, now we should add PV work here, because when fluid is entering, it is entering with some pressure volume and it is leaving out with some pressure volume. So that's why we need to add PV work to the, it represents the work necessary to propel fluids against the existing pressure. So that's why I can write it down as this difference of this plus Q plus W minus delta of PV into m dot. Now we know that U plus PV is H. So our first law of thermodynamics for open system, it becomes d of mu by dt of control volume plus delta of H plus half of U square plus GZ is equal to m into m dot is equal to q dot plus w dot. So this we have already studied. And for steady state, this term is 0, so we are only left with this. So at steady state, what is going to happen? There is no this term is going to be 0 with time. So we have only this delta of h plus half of u square plus gz into m dot is equal to q dot plus w s dot. So if I divide by m dot, so I will just left with q plus w. So delta h plus half of u square plus g into delta z is equal to q plus w. And if there are no velocity or elevation changes, then we can say for open system delta h is equal to q plus w. For closed system, it is delta u is equal to q plus w. This is basic thing that we have already studied in our previous classes. Okay. So that is what this equation is written. D of mu by dt is equal to delta of h plus half of u square plus gz, d mu by dt plus delta of h plus half of u square plus gz is equal to dq by dm plus dw by dm. Okay. So let's say from here I want to derive the Bernoulli's equation. So in case of Bernoulli's equation, when we want to derive it, it has some assumptions associated with it. So the assumptions are there are no heat or work interactions present in the system. So this dq by dm terms goes to 0 and dw by dm terms goes to 0. It is for steady state, so this term is also going to be 0. Now we are only left with delta of h plus half of u square plus gz is equal to, this term is equal to 0. So h2 plus half of v2 square, u I have written as velocity as v here. So h2 plus half of v2 square plus g into z2 minus h1 plus half of v1 square plus g into z1 is equal to 0. Then h2 minus h1 plus half of v2 square minus v1 square plus g into z2 minus z1 is equal to 0. So I can write it down as dh plus d, this is volume change. So dv square by 2 plus j into dz is equal to 0. Now we know that dh is equal to tds plus vdp. Okay, so can we use it here? So we know that the flow is inviscid flow. For assumption in Bernoulli's law, the flow is inviscid flow, so there is no friction we are considering. So when it's no friction, it is considered a reversible adiabatic flow. And when it is reversible adiabatic flow, you know the second law of thermodynamics, ds is equal to dq by t. When it is reversible adiabatic flow, therefore dq is equal to 0. If dq is equal to 0, then ds should be equal to 0. So it is called isentropic flow. Okay, so we have this term ds is equal to t ds plus vdp. So we are considering, if we are considering this inviscid flow, so no friction, meaning there is no entropy change. So ds is equal to 0. So ds is equal to vdp. So v volume, molar volume, I can write it down as 1 upon rho, correlating it with density. So ds is equal to dp by rho. So my Bernoulli's equation is dp by rho plus d into v square by 2 plus g into dz is equal to 0. So this is something that we have already derived in fluid mechanics. In your fluid mechanics class, you must have already derived this, but this derivation here, it is from first law of thermodynamics. Okay, so now let's try to move ahead. There are some various concepts we have not studied, but those are part of undergraduate chemical engineering thermodynamics. So we will start with something very important, that is called throttling devices. So this chapter is called application of thermodynamics to various flow processes. Okay, so the first one is throttling device. So what does it say? So when I am expanding a compressed gas adiabatically and slowly through a flow resisting device like some porous plug or throttling device, what happens? It undergoes some pressure drop without doing any work. So volume remains constant. We will see this experiment and then we will be able to relate it very well. So what is it saying? When a compressed gas expands, gas is expanding adiabatically meaning there is no heat loss to the surrounding, or q is equal to dq is equal to 0, expands adiabatically and slowly through a flow restricting device like porous plug or throttling device. What is going to happen? It is going to undergo a significant pressure drop without doing any work. So what is going to happen because of pressure drop? As a result, it is going to experience a change in temperature because pressure is dropping. So there should be some change in temperature which varies in magnitude and sign. Okay, so this involves, so what can be the temperature change? It can be either temperature can increase or temperature can reduce. So this involves either heating up or cooling down depending upon the nature of the gas. Okay, so this process accompanied by a change in temperature resulting from a reduction in pressure is known as throttling process. So what we did, we took some compressed gas, then we passed it through a flow resisting device. So what is going to happen? There will be some pressure drop without doing any work, and because of the pressure drop, the gas is going to change its temperature. So this process where the change in temperature is occurring because of reduction in pressure is known as throttling process. So this validity of this process principle, it was first tested by Joule and Thomson in 1862 by conducting an experiment which involved forcing a gas through a porous plug, and they observed the change in temperature produced by free expansion of gas. So, and they obtained a cooling effect. So this we are going to see now. So this effect is called Joule-Thomson effect. So this is their experiment. So this is some thermal insulation. That's why there is no heat flow through the system. It's dq is equal to 0. So what we did, suppose the volume V1 of a gas under constant pressure P1 is allowed to pass through, let's say this is some porous plug. So I am allowing my the gas of temperature is T1. It has P1 pressure and V1 volume. I am going to allow it to pass through this porous plug or throttling device. So that is passing from left region to the light region to the right region, where here pressure is my P2 pressure. Okay, the volume of the gas becomes V2 at the final state, which is shown by the dotted line. So volume is also going to change. Now what is going to happen? The gas flows from what is this phenomena? When I am passing my gas from this porous plug, it is obviously going to get some pressure drop. So it is passing from high pressure region to a low pressure region. So the process is carried out in an experimental setup where two frictionless pistons move slowly and the entire system is thermally well insulated. So what is it going to be? Work done by the piston in left chamber, that is equal to P1 V1, and in the right chamber W2 is equal to P2 V2. Okay, correct. So here my work is, it is at system, it is at some pressure P1 with volume V1, and at right side it is at pressure P2 with some volume V2 where P2 has reduced. Okay, so work done here is P1 V1 and here it is P2 V2. Now from the first law of thermodynamics we know that du is equal to dq plus dw. So dq is equal to du. dq is equal to du plus here work done by the system is taken positive. That's why we have this equation dq is equal to du plus dw. If you take work done by the system negative, here it will be minus P1 V1, here it will be minus P2 V2, here there will be minus sign, then automatically here it will cover up. So 0 is equal to du plus dw. So u2 minus u1, let's say if I'm taking here negative, so it will be w2 minus w1. So u2 minus u1 is equal to negative of w2 minus w1 or positive of w2 minus w1. So if I'm taking positive w2, that meaning work done by the system will be minus p2 v2 here and here p1 v1. So it anyway we end up at the same expression, that is u2 minus u1 is equal to p1 v1 minus p2 v2. Okay, let's not fall into these sign things. Work done by the system positive, negative. We have this dq is equal to du plus dw from the first law of thermodynamics. Now we know that this Joule-Thomson expansion is carried out adiabatically. So there should be no term of q. So dq is equal to 0. So we have 0 is equal to du plus dw. So 0 is equal to du delta u u2 minus u1 plus w delta w w2 minus w1. So u2 minus u1 is equal to minus of w2 minus w1. So minus of W2 is equal to P2 V2 and W1 is equal to P1 V1. So this is U2 minus U1 is equal to P1 V1 minus P2 V2. Now if I take all the terms together, so U1, if I take U1 this side, so U1 plus P1 V1 is equal to U2 plus P2 V2. Now we know that what is U1 plus P1 V1, it is H1, and what is U2 plus P2 V2, it is equal to H2. So we know that U2 plus P2 V2 is equal to U1 plus P1 V1. What does this mean? This means that H2 is equal to H1. If H2 is equal to H1, what does this mean? This means that delta H is equal to 0. Correct. So there is no change in heat content or enthalpy in the adiabatic process, adiabatic expansion of gas through the porous plug, and thus Joule-Thomson expansion is an isenthalpic process. Why isenthalpic process? Because we are obtaining delta H is equal to 0. There is no enthalpy change through this process. That's why we are calling that delta H is equal to 0. So now, okay, let's first go through again what we did. We had some porous plug through which we are passing some gas. So gas initially was at P1, V1, T1. So because of porous plug, there is going to be some pressure drop. So we have P2, V2 and temperature is going to change. We don't know currently if it is going to increase or decrease, but it is cooling effect studied by Joule and Thomson. So it is going to be P2, V2 and T2. So initially the work done by the gas is P1, V1, that is taken positive, and final is P2 V2. So if I apply first law of thermodynamics, it is dq is equal to du plus dw, and dq is equal to 0 because we are considering adiabatic expansion. So 0 is equal to du plus dw. So if I combine the terms, I get that H2 is equal to H1. So delta H is equal to 0. So Joule-Thomson expansion is an isenthalpic process. Okay, now what is Joule-Thomson coefficient? So whether a gas will produce heating, so we know that temperature is going to change. So is it going to increase or is it going to decrease? So whether a gas will produce a heating effect or is it going to produce the cooling effect during this Throttling expansion can be better explained by this Joule-Thomson coefficient, and it is defined, it is symbolized by mu Jt, and it is defined as the rate of change of temperature with respect to pressure at constant enthalpy. Constant enthalpy is very important because Joule-Thomson process delta S should be equal to 0. So it is defined as change in temperature with respect to change in pressure at constant enthalpy is known as Joule-Thomson coefficient. Okay, so very easy things. So let's say mu Jt is positive. So when will it be positive? When delta P is negative. Delta P is going to be negative and temperature is also going to be, delta T is going to be negative. Then only Joule-Thomson coefficient is going to be, so see, delta P is always going to be negative, correct? So if delta P is negative, this is always going to be negative because what does it say? It reduces the pressure. So when delta P is negative, correct, delta P is always negative. And let's say if I'm saying delta T is also negative, negative meaning it is cooling. So when it is cooling, so these both are negative, so mu Jt becomes positive. Now when mu Jt will become negative? When delta P is negative but delta T is positive. Then mu, here it's a mistake, it should be delta P is negative and delta T is positive. So that's why it is going to imply the heating effect. So this is always negative, but if this is positive, then Joule-Thomson coefficient is going to be negative. Then we need to remember this, when Joule-Thomson coefficient is positive, it is going to imply the cooling effect, and when Joule-Thomson coefficient is negative, it implies the heating effect. Now when Joule-Thomson coefficient is 0, so 0 meaning, what does 0 mean? This is always negative, but when this delta T is 0, then mu Jt is 0. So it implies no change in temperature. So it is not going to have cooling or heating. So the temperature at which no temperature change occur is known as inversion temperature. No temperature change meaning it is going to remain as it is. So the Joule-Thomson coefficient is employed for liquefaction of gases as well as the production of low temperature. So this mu Jt is less than 0. Less than 0 meaning producing heating effect for H2, helium, neon gases. So let's say when I'm reducing my pressure, so this mu Jt is negative for these gases, and when I'm further reducing, so mu Jt is becoming positive. Sorry, mu Jt negative. Mu Jt negative meaning heating effect and mu Jt positive meaning cooling effect. So at this temperature, this locus of points is known as inversion point where my Joule-Thomson coefficient is going to be 0. Okay, so this is negative, this is positive. Positive meaning cooling effect, negative meaning heating effect, and at this line it is equal to 0. So we defined Joule-Thomson coefficient as del T by del P at constant enthalpy. So I know that I can write down enthalpy as function of temperature and pressure, and we have derived this expression in our previous classes where we say that dH is equal to Cp dt plus V in V minus T del V del T at constant pressure dP. Okay, now what do we know for Joule-Thomson effect when it is going to be Joule-Thomson expansion? This it is going to be isenthalpic process. So that's why for that process dH is equal to 0. That's why we are left with 0 is equal to Cp dt plus V minus T del V del T at constant pressure dP. Okay. Yeah. Now from Maxwell relation, we know that dH is equal to Tds plus V dP. So I can write down as del H by del P. What I am doing, I am differentiating this equation with respect to pressure at constant temperature. So it will be with pressure at constant temperature. So T constant, del S del P constant temperature plus V into dP is 1. So this term. So del S by del P at constant temperature is equal to minus T. From the Maxwell relation, we know that del S by del P at constant temperature will be equal to del V by del T at constant pressure. So it is going to be del V minus T del V del T at constant pressure plus V. So what can I do? I can replace this term. Okay. Now So uh, uh, this term this term is nothing but del H del T constant del H del P at constant temperature. Del H del H del P at constant temperature. Correct. Now we had this equation this. So what we can write? We can write it down as 0 is equal to Cp dt plus this term V minus T del V del T at constant pressure is nothing but del H by del P constant temperature dP. Okay, so this term we replaced V minus T del V del T at constant pressure. We replaced it with V minus T del V del T constant pressure. This term we replaced it with del H by del H del P at constant temperature. So if I put it here, so I have 0 is equal to Cp dt plus del H del P constant temperature dP. So Cp dt is equal to minus del H del P at constant temperature dP. So I can write it down as del T by del P at constant enthalpy because dH is equal to 0. That is equal to minus del H del T at constant temperature divided by Cp. Correct. So I am just doing this term is coming this side. Del H by del P constant enthalpy is equal to del T by del P at constant enthalpy is equal to minus del H by del P. Sorry, it should be here P minus del H by del P at constant temperature divided by Cp. Okay. So what can I write? I can write it down. My Joule-Thomson coefficient was del T by del P at constant enthalpy that I can replace it with this term V minus T del V by del T constant pressure minus V divided by Cp. Okay. So this is what we are just replacing. It should be P here. There is one mistake. So yeah. Okay. So this is our term. Now let's say I'm dealing with ideal gas. Okay. Okay, let's try to revise what we did. We first, after we defined our Joule-Thomson coefficient as del T del P at constant enthalpy, then we saw that when mu or Joule-Thomson coefficient is positive, it implies cooling effect. So this is always negative. So if it is positive, then this del H should also be negative. So del H negative meaning temperature is reducing. So it is going through cooling. Similarly, when let's say if this is negative and this is positive, so mu is going to be negative. So if delta T is positive, meaning it is final temperature is increasing. So it is giving us heating effect. And then when mu Jt is equal to 0, so no temperature change. So the temperature at which no temperature change occurs is known as inversion temperature. So this is the plot. This is inversion temperature, negative, positive, and then we derived this expression. Okay. And this term is nothing but del T del P at constant enthalpy, negative of this. So this term. So we replaced it in this equation and we get that Joule-Thomson coefficient is nothing but, it's a mistake, it should be P here. Okay. It should be P here. If it is P here, so it is this term here. So it is just T into del V del T at constant pressure minus V divided by Cp. So this is called Joule-Thomson coefficient. So what is it going to be for ideal gas? For ideal gas, PV is equal to RT. Correct. So V is equal to RT by P. So del V del T at constant pressure. I'm differentiating with respect to temperature, keeping pressure constant. So R by P constant, differentiation of temperature is 1. So we are left with R by P term. So mu Jt, Joule-Thomson coefficient, is equal to T into this del V del T at constant pressure is going to be R by P minus V. So what is RT by P for ideal gas? RT by P for ideal gas is V. So V minus V by Cp. So that is going to be 0. So that's why Joule-Thomson coefficient is equal to 0 for ideal gas. Okay, so this is all about Joule-Thomson coefficient and it has many applications. So we took one compressed gas, we passed it through some porous plug. So because of that, because of passing through porous plug, there is going to be some pressure drop, and because of pressure drop, we are going to experience some temperature change. So this effect is known as Joule-Thomson effect. And here initially we have P1 V1 work, and final work is P2 V2. And if we apply the first law of thermodynamics, then we will have H2 is equal to H1, where delta H is equal to 0. That is called isenthalpic process. So there is no change in heat content or enthalpy in adiabatic expansion of gas through a porous plug, and that's why Joule-Thomson expansion is an isenthalpic expansion. And then we define Joule-Thomson coefficient mu as del T, del P at constant enthalpy. It can be positive or negative. Positive meaning it is going through cooling, negative meaning it is going through heating. And when it is zero, there is no temperature change, neither heating nor cooling. And the temperature at which this phenomena occurs is known as inversion temperature. Then we derived the expression that del T del P at constant enthalpy, we can replace it with this term T into del V del T at constant pressure minus V divided by Cp. And when we replace this term for ideal gas, we find that mu Jt is equal to 0 for ideal gas. Guys, I'm sorry, just give me a minute. Okay, this mu Jt is equal to 0 for ideal gas. Now let's try to have a look at some applications of this process. So we have one turbine or expander. So what does this do? Turbine consists of alternate sets of nozzles and rotating blades through which vapor or gas flows in steady state expansion process. Okay, so it has some blades and nozzles, and through which when we pass the gas, so it flows and it expands. That's why it is called expander. The overall result is the conversion of the internal energy of a high pressure stream into the soft work, correct? This is the use of turbine. So when steam provides the motive force, as in a power plant, the device is called as turbine. Or when it is a high pressure gas, such as some other gases other than steam, it can be ammonia or ethylene, ethane in a plant. So that device, then it is called the expander. Okay. So according to the first, if I apply the first law of thermodynamics for this open system turbine, so we have this, we are at steady state. So we have this equation delta of m dot into h plus half of u square plus gz is equal to q dot plus w dot. Okay. So potential energy, let's say this is my steam, superheated steam at temperature P1 T1. It is passing through turbine. So it is giving some soft work Ws P2 T2, and it is forming because of reduction in pressure. It is going from superheated to saturated steam. Okay, so what we can neglect, potential energy term can be omitted because there is little change in elevation. There is no or very little change in elevation, so this term is not going to give any significance. So gz is 0. Q can be neglected because in any properly designed turbine, so heat transfer is negligible, so Q is also is equal to 0. Then kinetic energy term can also be neglected because the inlet and outlet pipes sizes are same, so that's why there is no velocity change. Okay, so those are roughly equal. So this term is 0, this term is 0, Q is 0. But what we are getting some soft work. So W cannot be 0. So the first law of thermodynamics for turbine can be reduced to m dot delta S is equal to Ws dot. So Ws dot is equal to m dot delta S is equal to m dot into H2 minus H1. Okay. So here what do we know? We know the T1 and P1 at inlet conditions and P2 at outlet conditions we know, but we don't know what is H2 and what is Ws. So how to find this? So if the fluid in the turbine expands reversibly and adiabatically, the process is isentropic. So we have this process at P1 we have H1S1 and P2 we have H2S2. So it is going from P1S1 to P2S2. So that is my actual value of delta H. But we don't know what is H2, we don't know what is W, we don't know this term, what we don't know this term. So we have to find some way to establish the H2. So what do we do? Instead of following H1 S1 to H2 S2, we are following from H1 S1 to H2 prime S2, where we are knowing the pressure. Okay. So if the fluid in the and this S1 is equal to S2 prime, this entropy is remaining constant. So if the fluid in the turbine expands reversibly and adiabatically, so this we know reversible adiabatic process is also isentropic process. So that's why S2 is equal to S1, and this equation we can write it down as Ws is equal to this delta Hs. Correct. When if the turbine were isentropic, if the process were isentropic, but in reality it is not. The shaft work Ws isentropic is the maximum work that can be obtained from an adiabatic turbine with given inlet conditions and given discharge pressures. So this is the maximum we can do, but in reality we are not going to get that. So we define the efficiency. Actual turbines produce less work because the actual expansion process is irreversible. So we get eta is equal to Ws actual process where it is going from H1 S1 to H2 S2 divided by delta Hs where it is going from H1 S1 to H2 prime S1. Okay, so eta is equal to delta H divided by delta Hs. And generally the efficiency of turbine, it varies from zero point 0.7 to zero point 0.8. Okay, now there is one very important thing to note here. We know that initially we had superheated steam, but when it produces some work, so it is going to be converted into saturated steam. So uh, what is it going to be the quality of steam? That is something we are supposed to know. So here the steam is superheated, which produces work and becomes saturated. So some liquid will be formed that will be in equilibrium with gas. So total enthalpy H2, this H2 enthalpy it is equal to liquid enthalpy. It is consisting of outlet is in equilibrium. It is forming superheated to saturated. So it is going to be in equilibrium with vapor. So total enthalpy will be liquid enthalpy plus vapor enthalpy. So we can replace it with H is equal to liquid plus vapor. So in similar way, I'm writing it for some any property M, that is going to be XL liquid mole fraction into ml, that particular property, plus xv into mv. This is from Lever rule. So XL is 1 minus xv into ml plus xv into mv. So ml minus ml xv plus mv xv. So m is equal to ml plus xv mv minus ml. So we can say that h is equal to hl plus xv into hv minus hl. Correct. So what do we do here? In reality, we have this H1 S1. So from that, for the temperature and pressure from this kind of steam table, I will show you. So chemical engineering, thermodynamics. Yeah. So what is the actual process? Let's try to take one example of this turbine to understand how do we calculate it. So this turbine, there is one example given here. So see, inlet conditions, we know 8600 kilopascal and 500 degrees Celsius, and we know the discharge pressure and efficiency. So what can we do? So we are initially at this stage H1 and S1. So P1 at particular T1 we can find out this H1 S1, that I will show you from steam table. We can do that. So we have H1 and S1. Now for this isentropic path, S1 is equal to S2 prime is equal to S2. Correct. So we know the S2 prime, correct? And applying, if we apply the Lever rule, so we have this total entropy and at particular pressure 10 kilopascal. uh, we can find the at 10 kilopascal we can find the liquid and vapor entropy. So if we put this, so we can find the quality of the steam. Then that quality, if I put here for this H2 prime equation, so I can find out what is delta Hs, and from equation I can find delta H. From delta H I can find actual H. From actual H I can find quality. Again quality. Correct? So it is bit confusing you may seem. So what do we do here? First I have at temperature pressure, so I get H1 S1 value. Now from H1 S1 we have S1 is equal to S2 prime. Okay. So what do we know? S2 prime is equal to S2 liquid. This equation we know that S2 prime is equal to S2 liquid plus X2 prime, S2 vapor minus S2 liquid. So we know that we are at 10 kilopascal. So at 10 kilopascal, we know these two properties S2V, S2L. So from there, we can find X2 prime. Quality of the steam we can find. Then if I put this quality of steam in this equation, H2 prime is equal to H2L, because see at 10 kilopascal, I know H2L, H2, and if I am knowing X2 prime, I can find H2 prime. And if I know this H2 prime, then I can find out delta Hs. Now what is turbine efficiency? Eta is equal to delta H by delta Hs. So delta Hs I know, eta I know. So I know delta H. So delta H is nothing but H2 minus H1. So if I know delta H, then I can find H2 minus H1 is equal to delta H. So I can find out what is actual value of H2. Correct? Now if I know actual value of H2, I can find actual value of H2 also. Correct? So H2 I know. So for that actual H2 at 10 kilopascal, I can find out the quality of steam. And if I put it back again, then I can find out the quality of, I can find out the entropy of the this turbine process. Okay, so this is slightly, it looks confusing, but it is not. And okay, one more thing to see how can we find out these numbers. So, okay, let me open this in the another book, another tab. So see if I am opening it here, I will just show you some steam tables. It is loading. So see, these are steam tables. Okay. Can I do this? Yes, I can do this. So see, it is still loading. Huh. So we have this property of superheated steam. So from here, from property of superheated steam, at some 10 kilopascal, what the pressure we had? We had temperature of this 500 degrees Celsius and 8600 kilopascal. So if I, okay, it is still loading. So see here for superheated steam, 8600 kilopascal and 500 Kelvin. We have these properties. Sorry, 500 Kelvin is not. Uh, sorry, 500 Kelvin is not here. 500 Kelvin is here. 500 Celsius. Sorry, not Kelvin. We are at 500 Kelvin, right? Sorry, we are at 500 Celsius. Okay. So see here, 500 degrees Celsius and 8600 kilopascal. So we know this value of H, 3391.6. So it is 3391.6 kilojoules per kg. And S, I know S, what is S value at 500 degrees Celsius? This one, 6.6858 kilojoules per kg. Okay, so now the process is isentropic. So we go from S2 is equal to S1 is equal to S2 prime. So at 10 kilopascal, we know that steam is wet. So the superheated table is not going to help. Now we need to go to saturated table. Okay, it is loading. It is 10 kilopascal. Sorry. It is 10 kilopascal. So we need to find out 10 kilopascal. So see here, somewhere approximately here 10 kilopascal. Sorry, this thing. So this at 10 kilopascal. It's not going to, I'm not able to change it. Okay, I'm doing both this. So at 10 kilopascal, this one is U, this one is H and S, we know, right? So H can be something. Wait. This. Okay. So this is entropy. So it is something if we need to interpolate between 9.582 and 10.09, or you can just take the value at 10.09. So what they have done for entropy, it is they have taken at 0.6493, something in between these two for liquid and something in between these two for vapor, or you can just take those numbers, and we know the isentropic process, so we can find the quality. Now if I know the quality, and this 10 kilopascal, I know these enthalpies also, right? 2392.5 and 2585.1, 2593.1, and sorry, this value, something between these two and something between these two. So from there, I find out the isentropic enthalpy. So from enthalpy H2 prime, I know H2 prime. So delta H is H2 prime. This figure delta H is H2 prime minus H1. So I can find out delta HS. I have delta HS. So delta H is equal to eta into delta HS. So eta is we have given only, it operates at 75%. So 75 into this negative number, it is minus 955.6. So my delta H, now here we know delta H. So delta H is H2 minus H1. H1 we know. So H2 is equal to this 2436.0 kg. So now we know 2436. Here we know this 2436 instead of H2 prime. The ideal value should have been 2117, but we are getting 2436, and we put these numbers here so we can get actual quality of the steam, that is 93% coming out, 94%. And with this 94%, I can find out the entropy. Okay, so I hope this is clear. This is a very nice piece of works, piece of problems. These are not going to be this can be in your gate work, just they can give you all the data and you just have to find out what is the final enthalpy or final entropy. Okay, so this is all about turbine. Now there is something reverse thing to turbine, that is compressor. So what is compressor? So the compressor is a mechanical device that increases the pressure of a gas by reducing its volume and finally increases the temperature. So compressor meaning it increases the pressure and it reduces the volume and it increases the temperature of gas. Okay. So it is just reverse to the turbine, that we have some soft work and at saturated steam we are converting it into some superheated steam. Okay. So in a compression process, the isentropic work is the minimum shaft work that is required. Here it was maximum that can be done. So if the process is reversed, then it should be the minimum that is required. And if that is done, that is there, then only we can compress the gas. So minimum shaft work required for compression of a gas from given initial state to a given discharge pressure. So efficiency will be delta HS by delta H in this case. So here we have at compressor, meaning pressure is increasing. So we know that H1 S1, and we know at temperature T1 P1 to we are going T2 P2. So we know this H1 S1. So and we need to know H2 S2. So we follow isentropic path. Similar thing we do here also. I don't know if there is some example on expander. Okay, we don't have anything. This is compressor. Okay, let's see if problem. Yeah, it is given. So what is given? We are given that saturated vapor steam at 100 kilopascal is compressed adiabatically to 300 kilopascal. So we are going from 100 to 300 kilopascal with efficiency 0.75. So what is the work required? So we are at 100 kilopascal and 100 kilopascal. So this thing compressor, we are starting with saturated steam. So we need to follow the table of saturated steam. So 100 kilopascal, we need to know this term, 100 kilopascal. So we won't have exactly 100. So we have 101.33. So what you can do, if you can directly take 100 or you can extrapolate it. So you have 97.76 and 101.33. So you can extrapolate. So after extrapolation, you get S1 is equal to, S1 should be something 7.367 and 7.35, something in between. It is 7.3598, and H1 can be similarly this 2676 and 2674. Sorry. 2676 and 2674 in between. So this value is taken. So now what do you know? You know this H1 and S1. Now you will follow the isentropic path, correct? So you know this S2 S1 is equal to S2 prime, correct? And you know the final pressure, that is, sorry, you know the final pressure, that is 300 kilopascal, and 300 kilopascal, uh, it is superheated, correct? So at 300 kilopascal, we need to have a look at the superheated steam table, right? These tables. Sorry, it is loading. It is taking very long. So we are at 300 kilopascal, right? So this 300 kilopascal, and sorry, yeah. So 300 kilopascal, we have this value saturated liquid vapor. So we put this 27. Okay, they have not shown the calculation. So you get H2 prime is equal to this from the similar way. Then you get delta H. From delta H, you get H2. And from H2, you get this S2. Okay. So this is how you can use the turbines and compressor problems. These are very important problems in terms of industrial applications. Okay. So, okay, now let's try to move ahead to pump. So what is the use of pump? Okay, we had look at first turbine. So what does turbine do? It converts superheated steam into saturated steam with W is equal to m dot delta H, and you know H1 S1. From H1 S1 you are going to H2 S2, so you need to follow isentropic path, and then from isentropic path and from efficiency you can find out H2 and S2. So this is the maximum work that can be shaft work that can be obtained from an adiabatic turbine, but in reality you cannot obtain that maximum, so you need efficiency factor. Now similarly for compressor you are starting with saturated steam, and with some shaft work you are increasing the pressure, reducing the volume and increasing the fluid temperature, correct? So in that case you need to know eta is equal to delta hs by delta h. So you are at this p1 to p2 h1 s1 line, you need to go to h2 s2 line with this isentropic path h2 prime s2 prime. Okay, so this is all about turbines and compressor. Okay, let's try to move ahead to pumps. So what is the use of pumps? So pumps, liquids are usually moved by pumps which are rotating equipments. So for isentropic process, we know dH is equal to TdS plus VdP. This dH is equal to, sorry, where did it go? TdS plus VdP, and if it is isentropic process, then dH is equal to VdP. Correct. So W isentropic will be integration P1 to P2 VdP. Here only liquid is transported, so there will be no phase change. Okay, this is very important. Pump we are only using to transport liquid, so there is not going to be any phase change. So these are the standard formula for enthalpy change. dH is equal to Cp dt plus V into 1 minus beta T dP. Beta is isothermal compressibility, that is something for liquid is need to be known. Similarly, ds is Cp into dt by T minus beta V dP. And beta is called volume expansivity, not isothermal compressibility. It is K kappa. So this beta is called volume expansivity. So because the temperature changes in pumped fluids are very small, temperature change are really going to be very small. And because the properties of liquids are insensitive to the pressure, these equations are usually integrated on assumption that Cp, Cv, CPV beta those remains constant. So we just get equation as delta H is equal to, we don't need to integrate it over pressure, because this property Cp, this volume, beta, they don't change significantly with pressure. So we are just left with equation as delta H is equal to Cp into delta T plus V1 minus beta T delta P, and delta S is equal to Cp dt by T is ln T2 by T1 minus beta V delta P. Correct? So if there is some, yeah, so water at 45 degrees Celsius and 10 kilopascal enters an adiabatic pump. Adiabatic pump meaning dq is equal to 0. If dq is equal to 0, ds is equal to 0. Correct. 45 degrees Celsius and 10 kilopascal enters an adiabatic pump and is discharged at a pressure of 8600 kilopascal. Okay. So liquid, I am passing my water at 45 degrees Celsius, 10 kilopascal, and it is discharged at 8600 kilopascal. We are assuming that efficiency of pump is 0.75. So what is the work of the pump? Temperature change of water and entropy change of water. So for this 45 degrees Celsius and 10 kilopascal saturated liquid water, it has volume. If we, I don't, what is temperature? 45 degrees Celsius and 10 kilopascal. So you need to take the average. Then you will know this liquid volume. It should be something 1.1010 45 46 1010 in unit of 1.010 in units of centimeter cube per gram. So per kg it will be 1010 centimeter cube per kg. Beta from literature it is 425 into 10 is to minus 6 Kelvin inverse, and Cp is equal to 4.178 kilojoules per kg Kelvin. Okay. So what is isentropic work? W is equal to M. W is equal to VdP. Correct. This delta H isentropic uh, work W is equal to VdP. So volume we know that is 1010 into delta P 8600 to 10. So it is 8600 minus 10 into 1010, that is kilopascal centimeter cube per kg. And then it is just converted it into kilojoules per kg by some conversion. So I'm getting 8.676 kilojoules per kg. Now delta H eta is equal to similar concept to the compressor, but only thing we are only transporting liquid. So eta is delta Hs by delta H. So you get delta H is equal to 11.57, that is actual 11.57. So now what you do, you put this 11.57 here. Delta H is equal to 11.57. Delta H is equal to 11.57 plus Cp. What was the value of Cp? 4.178. Cp delta T, Cp delta T plus V, volume is 1010. 1 minus beta is 425 into 10 is to minus 6. 1 minus beta T, temperature is 45 degrees Celsius, that is 318.15 Kelvin, into delta P. So delta P is 8600 minus 10, so it is 8590 kilopascal. So it is just unit conversion. So it is divided with 10 is to 6. So if I substitute and if I find delta T is just 0.97 Kelvin or 0.97 degrees Celsius. So we anyway say that there is no temperature change. And if I want to find delta S of this process, so delta S should be very less because we are considering isentropic VdP we used, right? So delta S is going to be very, very, very less. If it is less or not, let's try to confirm. Cp 4.178, ln delta T we know it is 90.97 Kelvin. So initially it was 318.15 Kelvin, and final will be 318.15 plus 0.97. So it is 319.12. So this is ln T2 by T1 minus beta, this value 425 to 10 is to minus 6. V is 1010 into delta P, similarly 8590 divided by 10 is to 6. So you see that entropy change is 0.009 kilojoules per kg Kelvin. So that is very less. Okay, so that's why we can say that the same equations apply to the NWD. Okay. So this constant S we can consider, and we can find delta H dH is equal to VdP. Okay, so this is what I wanted to show from the pumps. So these equations, these have some practical applications. Okay, so we learned about pump, we learned about turbine, compressor, and pump. Okay, so turbine, we have steam, superheated steam. It is going to saturated steam. We are following isentropic path. When you are following steam table, you need to remember that when you are starting with turbine, initial condition are superheated steam. So you need to have a look at superheated steam table. And at final condition, you need to look at saturated steam table. And for compressor, you are starting with saturated steam and you are ending at superheated steam. So you need to take, for inlet, you need to consider saturated steam table, and for outlet, you need to consider the superheated steam table. This is something you need to take care while taking the values. Okay, now and then pump we considered DH, delta H is equal to VDP. So delta H is work done. DH is equal to yeah. So this is the work done. Yes. And these equations we considered liquids to be incompressible. So this all Cp, V, beta, those are independent of pressure and we find out this term. So we had one example where we find delta Hs from here from delta H. We found delta T. Delta T was very less, 0.97 Kelvin. And from there we find delta H, it was coming out to be 0.009 kilojoules per kg Kelvin. So that's why we can use. So this ejector, what is the use of ejector? Ejectors remove gases or vapors from an evacuated space and compress them for discharge at a high pressure. So it just remove the gases and vapors from some evacuated space and it compress them for discharge at high pressure. So where it is required, it just transfer it at high pressure. So an ejector, it consists of an inner converging diverging nozzle uh, through which the driving fluid is fed and some outlet this outlet where outlet which is a larger nozzle through which both the extracted gases or vapors and driving fluid passes. Okay, so the momentum of high speed fluid which is leaving the nozzle is partly transferred to the extracted gases or vapors, and the mix velocity is therefore less than that of the driving fluid leaving the smaller nozzle. Okay. It is nevertheless higher than the speed of the sound, and the larger nozzle therefore acts as a converging diverging diffuser in which the pressure rises and velocity decreases passing through the speed of sound at the throat. This is not important right now, but yeah. Okay, so we have completed one very important part, that was throttling device. Let's first try to go through what we did. We had in earlier classes we had derived first law of thermodynamics for open system, and from there we tried to derive the Bernoulli law with assumptions that has that no heat work or no heat or no work interaction. So these two terms zero, steady state. So this term is also zero. Then we are only left with h2 plus half v2 square. This term is equal to 0. So h2 plus half v2 square plus gz2 minus h1 plus half v1 square plus gz1 is equal to 0. So h2 minus h1 dh, half of v2 square minus v1 square, it is dv square by 2. G of z2 minus z1, so g into dz is equal to 0. Now dh is equal to tds plus vdp. We know that the flow is inviscid flow in case of when we are considering Bernoulli's equation. So inviscid flow, no friction. So no friction, it is equivalent to reversible adiabatic flow. And when we say that the flow is reversible adiabatic, so it is isentropic flow. So this term goes to 0. So we are only left with dh is equal to vdp. So dh is dp by rho. So we are at Bernoulli's equation from first law of thermodynamics for open system, that is dp by rho plus d into v square by 2 plus g into dz is equal to 0. Then we quickly go through throttling device. So in throttling device, the principle is you pass a compressed gas from porous plug or some throttling device due to which it goes through some pressure drop, and because of the pressure drop, the temperature of fluid increases or decreases depending on the condition. So that's from there we derived the equation W1 P1V1 here and here P2V2, and from first law dq is equal to du plus dw. It is adiabatic arrangement, so dq is 0. So we are left with H2 is equal to H1. So delta H is 0, which is isenthalpic process. So throttling process is Joule-Thomson expansion is an isenthalpic expansion. And then we had a look at Joule-Thomson coefficient mu Jt. It is del T del P at constant enthalpy. So delta P is always going to be negative because it is always going to reduce. So if delta T is also negative, then Joule-Thomson coefficient is going to be positive. And if delta T is negative, meaning we have cooling effect. So when Joule-Thomson coefficient is positive, we have cooling effect. Similarly, when Joule-Thomson coefficient is negative, meaning if this term is negative but this term is positive, this term is positive, meaning we have heating effect. Then one more phenomena where Joule-Thomson coefficient is 0. So the 0 meaning no temperature change, and at that point it is known as inversion temperature. So this is the line of inversion temperature. This is Joule-Thomson coefficient negative. This is Joule-Thomson coefficient positive. Then we derived the expression and we find that mu can be written as T into del V del T at constant pressure minus V divided by Cp. And for ideal gas, this can be replaced by R by P, and R T by P is only V, so V minus V is 0. So we have Joule-Thomson coefficient as 0 in case of ideal gas. Then we have a look at turbine where we convert superheated steam to saturated steam. Generally know at T1 P1 we know H1, and uh, we know the final pressure. So based on that, we follow isentropic path. Then we try to find out H2 prime. From H2 prime, we know delta Hs. From delta Hs and eta, we know delta H. From delta H, we know H2. And from H2, we know S2. Okay. So from H2, we know quality, and yeah, and then we can find out S2. Then for turbine, it is the shaft work. Shaft work is the maximum work that can be obtained from an adiabatic turbine. And for compressor, saturated steam is converted into superheated steam, and we follow this path. This is just reverse of that. Then pumps, we consider W is equal to VDP, and then we use this equation, and we had one example where we see that delta T is neglected. We can neglect delta T, and we can delta S is also very very less, so we can take delta S is equal to 0. Okay, now this is all what we covered. Throttling device, Joule-Thomson porous plug experiment, turbine, compressor, pump, and ejector. Now let's try to, now we are going for the reaction part. So now let's try to have a look at some important terminologies. Okay, page number 51. Okay, so there are two types of heat, sensible heat and latent heat. So what is sensible heat? So sensible heat is the heat required to a system in which there are no phase transition, no chemical reaction, or no changes in composition that causes the temperature of the system to change. Okay, so no phase transition is very important. Phase transition, so it is this. So this is generally what we take. It is staying in liquid. If it is in liquid phase, it is staying in liquid phase. If it is in vapor phase, it is staying in vapor phase. So no composition change, no chemical reactions occurring. Okay. So Q is equal to delta H, which is equal to integration T1 to T2 CPdT. And it can be written as Cp of ideal gas by R is equal to A plus Bd plus Ct square plus D into T raised to minus 2. So ideal gas heat capacities increase smoothly with increasing temperature. Okay, toward an upper limit which is reached when all translation, rotation, and vibrational modes of molecular motions are fully excited. Okay, and from there I can find the value of Q as Cp dt. Okay, so this is the equation. If you integrate this is A plus Bt plus Ct square plus D into T raised to minus 2 dt. So A dt is A into T2 minus T1, B into T, T is T square by 2. So b by 2 t2 square minus t1 square plus c t square. So c t square is t cube by 3. So c by 3 t2 cube minus t1 cube plus t raised to minus 2 is 1 by t minus 1 by t. So it is minus d 1 by t2 minus 1 by t1. So from that you can find out q and mean heat capacity over some temperature. So you just need to divide this equation, divide by delta t. So this delta t terms cancel out and you are left with mean heat capacity. Then we will not go through some examples here. Then there is one more term, that is latent heat. So latent heat is when a pure substance is liquefied from solid state or vaporized from liquid state at constant pressure. There is no temperature change, but only phase is changing. So when a pure substance is liquefied from the solid state or vaporized from the liquid state at constant pressure, there is no change in temperature. However, the process requires the transfer of finite amount of heat to the substance. So these heat effects are called the latent heat of fusion or latent heat of vaporization. Okay, so heat required to transfer crystal structure from one solid state to another is called heat of transition. This is not something required for us. So there is one example of heat of transition where the heat absorbed when the rhombic crystalline sulfur changes to the monoclinic structure at 95 degrees Celsius and 1 bar is 360 joule for each gram atom. Okay. So this is heat of transition when we are going from one structure to another, where here the example is rhombic crystalline sulfur to monoclinic structure. Okay. And this latent heat, it is only function of temperature. So these things we have already seen. Clapeyron equation, delta H is equal to T delta V dp set by dt. Then this we have derived, so we are not going to have a look at here. This Troughton's rule, rough estimates, then Riedel equation also we have seen, Watson's equation also we have seen. Now the important terminology is heat of reaction. Okay, so let's try to have a look at this part. So heat of reaction. Okay. Okay, so see, chemical reactions, they generally are accompanied by the transfer of heat by temperature changes during the reaction or by both. The ultimate cause lies in the difference between the molecular configuration of products and the reactant. Okay, so how can we find out the standard heat of reaction? Okay, so heat of reactions are based on the experimental measurements. Wait, I want to show you something else. Okay. So Q is equal to delta H. So if Q is negative, then heat is removed from the system. So that's why we call the reaction as exothermic reaction. The other way, where Q is greater than 0, then heat is added to the system and it is called the endothermic reaction. So for this, there is one sample reaction. So what is standard heat of reaction? The defined, how is it defined? So the standard heat of reaction is defined as the enthalpy change when A moles of A and B moles of B in their standard states at temperature T. Standard state is very important. Standard states at temperature T react to form L moles of L and M moles of M in their standard states at the same temperature. Standard state is very important. So what is standard heat of reaction? It is the enthalpy change when A moles of A and B moles of B in their standard states at temperature T. These two reacts and form L moles of L and M moles of M in their standard states at the same temperature T. So this is called standard heat of reaction. So we are using one word, standard state. So what is standard state? A standard state is a particular state of a species at temperature T and a specified conditions of pressure, composition, and physical conditions. It's like gas. So for gases, for standard state is assumed as an ideal gas and the condition is 1 bar pressure and 298 Kelvin. For liquids and solids, those are assumed in the pure form and the pressure is generally taken as 1 bar pressure. Okay. Now let's say this kind of reaction. Uh, so this mode Vi, V1 A1 plus V2 A2, 4, let's say there are n number of reactants giving V3 A3 plus V4 A4 plus some other n number of products. So this mode of Vi is called stoichiometric coefficient. A1 is chemical formula of the compound. If V1 is greater than 0, so it is product. If V1 is less than 0, it is reactant. Okay. So the Vi with their accompanying signs are called stoichiometric numbers. So what is stoichiometric number of N2? It is minus 1. For H2 it is minus 3, and for ammonia it is 2. So it can be just standard heat of reaction can be just found as summation of Vi delta H of formation of that compound. So what is heat of formation of that compound? It is defined as the enthalpy change to form one mole of compound from its constituent and constituent elements. Okay, so if there is one example here, we can just have a look. So see, so this is standard heat of formation reaction. See, methanol. Methanol is consisting of carbon, hydrogen, and oxygen. So carbon plus half of O2 plus 2H2 gives C H3OH. So this is a formation reaction of methanol, but this H2O plus SO3 giving H2SO4, it is not formation reaction. It should be H2S and O2. From there it should form. Okay. I don't know if there is some example. So see how to find this delta H of reaction. So CO2 plus H2 giving CO plus H2O. This is the reaction. So we have this one reaction CO2 giving C plus O2. We know delta H. C plus half O2 giving CO. We know delta H. And H2 plus half O2 giving H2O. We know delta H. So what we do? This half this cancels out. C cancels out. So we are only CO2 plus H2. So we just need to do simple addition. So see, let's say I'm supposed to find the standard heat of reaction at 25 degrees Celsius for this following reaction. So HCl plus O2 giving to H2O plus Cl2. So we need to have a look at table C4. So let's try to have a look at table C4. So see, very important thing. Here it is written in gas phase. So we need to um, have a look at the gas states. Okay. Yeah. So we are having HCl plus O2. O2 has no standard heat of formation. So we will just find out for HCl in gas phase. This is very important to see. HCl in gas phase, it is minus 92307. So it is minus 92307 joules. O2 it is 0. H2O. H2O in which phase? It is in gas phase. So we need to find H2O in gas phase. So water is in gas is also there, liquid is also there, but we need to have a look at gas phase. So it is minus 241,818, very large value, minus 241,818 joules. Okay, so how do we write this reaction? 4HCl giving 2H2 plus 2Cl2. We have 4HCl. Okay, so we need to multiply this number with 4. And this 2H2 plus O2 giving 2H2O. Okay, so if these two cancels out, so we are only left with this particular summation. It is just simply you can just do H2O to H2O. So multiply this number 2 into this minus reactant. It is 4, so 4 into this. Okay, why we don't consider? Because these two O2 Cl2 they cancels out on both the sides. So that's why we don't need to consider. So HCl we are forming, but we have this minus 923074 2H2 plus 2Cl2 giving, we have H2 plus Cl, half H2 plus half Cl2 giving HCl, it is this. So, but we need HCl on this side. So it will be not negative, it will be positive, and we need 4 HCl. So it is 4 HCl giving 2H2 plus 2Cl2. And similarly for H2O, H2O is on right side. So H2 plus half O2 giving H2O, but we have 2 H2O. So 2H2 plus O2 giving 2 H2O. So that's why it is 2 into this. So if when I add these terms, I get the standard heat of reaction. Okay. Okay, now the standard heat of combustion. It is also similar. Only a few formation reactions can actually be carried out at conditions of interest, and therefore data for these reactions are determined indirectly. One kind of reactions that readily lends itself to experiment is the combustion reaction, and many standard heats of formation come from the standard heats of combustion measured using calorimeter. So calorimeter, it is just generally find at constant volume. So a combustion reaction is defined as the reaction of an element or compound with oxygen to form specified combustion products. For organic compounds consisting of carbon, hydrogen, and oxygen, the products are carbon dioxide and water, but the state of the water may be either liquid or vapor based on temperature. Here we had seen it is not a combustion reaction, but in that example it was a gas phase. This example, it's not that this is not a combustion reaction, but it is a gas phase. Okay, so that is important to know. So see this example, ethane, butane, C4H10. So 4C plus 5H2 giving C4H10. So this is not generally feasible. So what we do, we know for CO2, we know for H2O. And it is this one reaction, CO2 plus 5H2O, 4CO2, 5H2 giving C4H10. So from there we can find 4 carbon plus 5 hydrogen giving C4H10. Okay, then these tables are also there. So this 10 minus 1257904 butane. So see minus 12579. So this is combustion and this is standard heat of formation. Delta H naught also depends on temperature. So delta H, because Cp depends on temperature, and we had seen that temperature dependence of Cp. So delta H is integration Cp dt. So from there, delta H naught is equal to delta H naught naught plus this R T naught to T is delta Cp by T. These are very complex, not very complex, but you can't solve it pen paper. You need some things. So we are not having look at this part. We are leaving it. Okay. Okay. There was one more thing. This we have looked. This is the adiabatic flame temperature. Um, So the material of construction or of combustion chamber dictates maximum temperature at which combustion chamber can be operated. So that is basically given by adiabatic flame temperature. So it is important to know maximum attainable temperature when we are going to burn a fuel. So when a fuel is burned in air or oxygen under adiabatic conditions, to the temperature attained by the product stream is known as adiabatic temperature. So calculated temperature, this whatever temperature we are calculating uh, is maximum with assumption of adiabatic operation of burner. Note adiabatic we are already saying, so that should not be any heat loss, but in reality there are always heat loss. no dissociation and pure oxygen is used. It's not air, but it is pure oxygen. 100% oxygen is used. But in actual practice, we don't have all these things. We have excess air or oxygen present. Then reactants not in stoichiometric proportion. We have some compounds in excess. Ammonia N2 plus H2, 2 N2 plus N2 plus 3H2 giving to ammonia. So it's not stoichiometric, but we take some amount of H2 in excess. Then we don't have always excess complete reaction. We have incomplete combustion. Then CO2, it dissociates into CO and O2 at high temperatures to form equilibrium mixture of CO, CO2, O2, and there are always energy losses to the from the combustion chamber. And we also add inerts in some kind of reactions. And yeah, so this is one thing. Adiabatic flame temperature, it is the temperature attained when the fuel is burned in an air or oxygen under adiabatic condition. Okay, so this is all about today's session. So let's try to have a look at some one or two small problems before ending. Uh, Very simple problem we will take. Sorry. Here, this we had in last class, we had seen some problems till this problem is remaining. So let's try to solve this problem. Okay, so what this problem states, the molar volume of a binary mixture at temperature and pressure is given by V is equal to 120 x1 plus 70 x2 plus 15 x1 plus 8 x2 x1 x2. Find the expression for partial molar volumes of species 1 and 2. Okay, so how can I find partial molar volume? So what is the first thing I need to do? I need to convert whole thing in x1 or x2. So we will do it in terms of x1. So 120 x1 plus 70 x2 is 1 minus x1 plus this is 15 x1 square x2. So 15 x1 square x2 is 1 minus x1. 8 x1 x2 square x2 square is 1 minus x1 whole square. So this 120 x1 70 minus 70 x1 15 x1 square minus 15 x1 cube, and this 1 minus x1 square is 1 minus 2x1 plus x1 square. So this we need to expand. So we have this simple equation V is equal to 70 plus 58 x1 minus x1 square minus 7 into x1 cube. So what is partial molar volume of component 1? V1 bar is V plus x2 dV dx1. So dV dx1 will be 58 minus 2x1 minus 21 x1 square. So dV dx1 is this 58 minus 2x1 minus 21 x1 square plus x2 into x2 1 minus x1 plus V. This in terms of V. So we have V1 bar is equal to 128 minus 2x1 minus 20 x1 square plus 14 x1 cube. What is V2 bar? V2 bar is V minus x1 dV dx1. So V was this minus x1 dV dx1, and we just need to do simple math and we get this V2 bar. Now, so that when these expressions are combined for V is recovered. So what is V? V is x1 V1 bar plus x2 V2 bar. So am I able to recover this? So x1 into this V1 bar plus x2 1 minus x1 into V2 bar. So 120 x1 minus 2 x1 square minus 20 x1 cube plus 14 x1 is to 4 plus 70 plus x1 square plus 14 x1 cube minus 70 x1 minus x1 cube minus 14 x1 is to 4. So this terms 4 power cancels out. So first constant term is 70 power x1, it is this. So this gives 58 x1 power 2 minus 2x1 square plus x1 square, it is only minus x1 square power 3, so minus 6 minus 1 minus 7x1 cube. So is it recovered? So if we check the formula, 128 minus 2x1 minus 20, sorry, 70 plus 58 x1 minus x1 cube minus 7x1 cube. So we have recovered the equation. Now one more thing is asked to us is, so that these expressions satisfy the Gibbs-Duhem equation. Okay, so what is Gibbs-Duhem equation? Gibbs-Duhem equation is x1 into dv1 bar plus x2 dv2 bar is 0. So we find if this x1 d1 v1 bar by dx1 plus x2 dv2 bar by dx1 is equal to 0. If this equation is satisfied, then we can say that Gibbs-Duhem equation is satisfied. So we have v1 bar. So what is dv1 bar by dx1? This equation respect to x1, so it is minus 2 minus 40 x1 plus 42 x1 square, correct? And this equation 2x1 plus 42 x1 square. Okay, so x1 into dv1 bar by dx1 plus x2, that is 1 minus x1 dv2 bar by dx1. If I find it, minus 2x1 minus 40 x1 square plus 42 x1 cube plus 2x1 plus 42 x1 square minus 2x1 square minus 42 x1 cube. So if I combine this cancels out. This is minus 42 plus 42 cancels out, 42, 42, these two also cancels out, this is 0. So that's why we say that it satisfies the Gibbs-Duhem equations. Okay. Further, we have to show that dv1 bar by dx1 at x1 is equal to 1. So dv1 bar by dx1, this at x1 is equal to 1. So if I put 1 here, if I put 1 here, so it is 42 minus 40 minus 2, it is 0. That is equal to dv2 bar by dx1 at x1 is equal to 0. So if I put x1 is equal to 0 here, 0, so I'm only left with 0. So this also satisfies this equation, dv1 bar by dx1 at x1 is equal to 1, which is equal to dv2 bar by dx1 at x1 is equal to 0. Okay, so this was one very simple problem that we took. We will take more problems on Friday's session. We will take only problems on Friday's session. We are not going to learn any theoretical part on Friday's session. Okay, so thank you so much. We will meet in Friday's session where we will only be solving some problems, some example problems. So thank you so much for joining. If any one of you is having any query regarding this thermodynamics course, please feel free to ask me. Please feel free to write me on this particular email ID. I will try to respond as soon as I can. So thank you so much. Thank you so much everyone for joining.